Hello, today we will be trying to solve a Sudoku problem using a recursive backtracking algorithm in Python. For this video, we will be taking two Sudoku problems. One is an easy one, another one is a hard one. We will first solve the easy one using a simple algorithm, and then from there we will be solving the hard one using the brute force recursive backtracking algorithm. Now for our video, let us try to solve the easy Sudoku first. Now we'll be representing the Sudoku problem in this format, which is a 9x9 grid with zeros representing the blank spaces and the real numbers representing the initial input problem. Now our goal will be to find the right numbers to fill in each one of the zeros which have been mentioned here. The rules for solving Sudoku remain the same in this case, wherein there should be a unique number from 1 to 9 which should be filled in each one of the rows, and a unique number from 1 to 9 which should be in each one of the columns, and a unique number from between 1 to 9 which would be in each one of those 3x3 matrices which are 9 in number here, which means among the 0, 0, 3, 2, 5, 0, 0, 0, 0, which is the first quadrant, we should have a unique set of numbers ranging from 1 to 9. Before we start the actual solve, let us create a few tools that will be required for us, right? The first tool that will be required is some way to print this particular grid so that we will know that the problem is solved. The second tool that we will be needing is to check whether the problem is actually solved or not. Now to do this, there are two conditions which have to be met. The first condition is that all the zeros should become filled with any one number between 1 to 9. And number two, the rule that we actually spoke about, the vertical, the rows and the columns, as well as the 3x3 matrices that we actually have. And lastly, with both these tools, we will be able to solve the problem. Now let us start with just doing the first tool, which is nothing but displaying the grid. Now for this, let's create a new function called display grid, and this will be the structure for it. We just iterate through the entire grid line by line, and then for each line item, in case there is a 0, we print a dash, and if the item is present, we convert that into a string and then print it. Now let's just look at the second tool which we are going to be using, which is the computation of the possibilities, right? Now let us create a function called compute possibilities. For compute possibilities, we are going to use one parameter which is called grid. We are just going to pass this grid to it, and then we need to find out at any point in time what are the possibilities that are available for filling each one of the places where there is a 0. The first thing is we need to initialize a list of possibilities. We need a placeholder or a data structure for holding these possibilities. For that, let us initialize all the possibilities using another function. Let's call it initialize possibilities. Now we are calling a possibility as a list of lists of lists. Now what we are going to do is, for each one of those items which are there in this list of lists, we are going to initialize it with numbers between 1 to 9. And for that, we are going to use this list function and then a range function here. Now once this list of possibilities has been initialized, we will be returning this possibilities. Now coming back to our compute possibilities, the first step will be to get the possibilities initialized. Possibilities, initialize possibilities. This step is also important because every time we want to call compute possibilities, we want to reset all the possibilities. We want to reset this list back to its initial state, and that is why we will be using this function again. Now what we will be doing is we will be iterating through each and every row of this particular grid which has been given as a parameter, and we are going to check if the number already exists in either the row or the column or in one of those 9 3x3 grids. Then we are going to keep removing that item from the list. Now let's see how we do that. For I in range of 9, we are going to go from 0 to 9. For j in range of 9, again column wise we are going to go from 0 to 9. If grid of I j equal to 0, only then we are going to be checking what are the possibilities there. We will initialize one more variable called p. For p in range of 9, right? Now let's first check column wise. If grid of p j in possibilities of I j, then possibilities of I j dot remove, we will remove that item, grid of P j, right. Now let's check row wise. Same one, if grid of I P in possibilities of I j, possibilities of I j dot remove grid I P, right. Now comes the tricky part. We need to check in the 3x3 matrices. Check in 3x3 boxes, right. Now here we will need one helper function here. Now let's create a lambda for that. What we need to find out is, if we are between 0, 1 and 2, we need to be in the first box. If we are in 3, 4 and 5, we need to be in second box. And if it is 6, 7, 8, we need to be in the third box, and likewise, right. Now we need a mechanism to figure out how to convert each one of those boxes' locations into an ij coordinate. Now let's write this quick lambda for that. B min is equal to lambda, given x, we need x, the quotient of x divided by 3 and multiply it by 3. So we need a way in which we can convert the ranges between 0 to 3, 3 to 6, 6 to 9 into, by using the ij values, right. Now we'll see how to use this lambda function to do that. Now coming back to our possibilities function, now what we'll be writing is, for m in range of B min of I, comma B min of I plus 3, for n in range of B min of j, comma B min of j plus 3, if grid of m n in possibilities, the same condition again, possibilities of I j, then possibilities of I j dot remove grid m n. Now just let's take a second to understand what we just did here. Now we need to traverse through each one of the 003, 250, box, 006, 700, 230 boxes and so on. Now how do we get the coordinates, the I and j coordinates for traversing through that? That is where the bmin function comes in handy. Now when we are in I equal to 0 and j equal to 0, what we see is bmin of I, which is nothing but 0 divided by 3 is 0, the quotient is 0, multiplied by 3 is 0. So which means that I am getting the range, the first parameter for the range, which is 0. When j is 0, the same thing happens and we get plus 3. Now bmin of j is nothing but 0 plus 3, which is nothing but 3. Now when this function converts into for n in range of 0 to 3, similar thing happens for the m range as well. Now when we move to say 4, we need the range from 3 to 6, right? Now let us see how it works. If I equal to 4 and j equal to 4, now 4 divided by 3, the quotient is 1, multiplied by 3, it is again 3. Now if you are having 5, the same thing comes back to 3. Now we need this from indexes 3 to 5, which means that if it is 5, 5 divided by 3, the quotient is 1, and multiplied by 3 is 3, and when you add 3 to it, we again get back between 3 and 6. So this is the whole mechanism by which we will be able to use the least amount of code to check all those 9 boxes. Now that we have checked all the 3 cases, now let us return possibilities back. Return possibilities. Now the second function is also, helper function is also ready for us. Now we need to create one more helper function, which is called is correct or not. Now let's again create a new function called def is correct, and we'll pass the grid as an input to it, and we'll be checking if each one of the list items which are there in each one of the rows is having items between 1 to 9. We'll transpose this entire grid and see if each one of the transposed items, which is nothing but the columns, are having items between 1 to 9, and each one of the 3x3 grids is having 1 to 9. Now this is how the function will look like. Now we create a variable called trans list items, where we can convert each and every row in grid into a column, which is nothing but a transpose. That will give us a new list which is of all the columns one after the other. Now the quadrants, we will be using the function that we created recently, the lambda function, which is bmin. We'll again be following the same principle that we did there. So we'll just say quads is equal to grid of mn for m in bmin of I and I plus 3, and for n which is in the range of j and j plus 3. Now that we have the transposed list items and we have the quadrants, we'll just go and check if each one of the items between 1 and 9 is there in each one of these areas, and they must be present only once. So the condition will be for I in range of I 1 to 10, for q in quadrants, if q dot count is only 1, of I is only 1, then return true. In this case, we'll check for the opposite. We'll say if it is greater than 1, we'll return false. The second one is much easier. In grid itself, each row, we just check if each one of the items between 1 to 9 is occurring only once. And if it is occurring once, we return true. In this case, we return false. And the same for the transposed list items as well. Now let us just create one more tool just for our own reference, which is called is solved. Return not any of 0 in LST for LST in grid. Basically, it just says there should not be any 0 in that, and we're also going to check if it is going to be correct. Is correct. So basically, it just tells us if all the items in the grid are filled and if the grid is filled correctly, which is going through this algorithm. Right now, let's come back and then solve this particular problem. We'll create a new function called solve. Def solve. We'll pass the parameter g, which is nothing but the grid itself. Now here, there's a very important concept that has to be kept in mind. We need to create a copy of this entire grid for us to use. The reason is that Python uses pass by reference, and for our brute force recursive backtracking algorithm, we need to have a pass by value so that we will be able to go back to the original state when the recursive call was actually initiated, in case you want to do a backtracking. So what we'll do is we'll import a library called copy, from where we'll be using this deep copy mechanism to copy by value a complete where we'll be able to copy each and every single item of grid into another copy. So we'll call it grid is equal to copy dot deep copy of g. Now we'll be starting to use the grid variable for our algorithm, while not is solved grid. Let us compute the possibilities. Compute possibilities for this version of the grid. Now what we'll do is we'll check for each and every single item in the grid and see if the possibilities count is only 1, which means that there is only one item which can actually be filled in particular grid location, because of which it is very easy to solve it. For I in range of 9, we'll iterate through the grid. For j in range of 9, if grid of I j equal to 0, if len of possibilities of I j is equal to 1. Right? This is the only solution which is possible there. Then grid I j equal to possibilities of I j dot pop. Because we're using a list, so we'll just pop that. Now there's a chance that we might actually solve it incorrectly, and if there are no possibilities available for a particular I cross j location, it means that we have done something wrong in between and we need to come out of the loop. So we'll just check that other condition as well. If length of possibilities of I j is 0, this is a case where we have made some mistake, return false. We don't want to continue, right? And the while loop keeps continuing and running. We'll display the grid if it is solved and return true, right? Now let's see if this works. Right, let's give it a easy problem. We'll say grid is equal to grid easy. We'll display the grid initially before solving it, and then we'll solve it. We'll save this file. Now let us extend this particular problem to a hard Sudoku and then see how the algorithm has to be modified to take care of that. Now we'll create a new problem statement for doing the hard problem. We'll call it grid hard 2 and let's pass as an input to it. For us to solve this problem, we need to make a few corrections or enhancements to the code. Let's see what all have to be done. First thing is, in our solve, it is not going to be solved very fast. It has to be, first thing that we need to change is in our solve algorithm, where the while loop will not actually get completed. So we need to have a way in which we have to figure out that even after filling all the locations where there's only one possibility, the solution has not come out yet. So let us create something called the compare grid. Is equal to copy dot deep copy grid. We will be doing a check if the state has not changed even after a complete iteration. Now we'll write the condition here. If grid equal to compare grid, then what it basically means is don't continue doing this, just come out of the loop. And then let's do the next step, which is to solve the hard problem. Now we had an if condition which said if it is solved, we return true. If it is not solved, it's a hard problem. Okay, here is where we're going to use a recursive backtracking algorithm. What we will do is we will iterate through the entire grid once again, and every time we encounter a location where there is more than one possibility, we take the first possibility, put it in, and then try to solve it. Now this solve is the recursive call here. Now what happens is, every time we choose a new possibility from the list and try to solve it, it goes deeper and deeper and deeper until it has a solution. If there is no solution, it returns false either here, or it returns false because the solution is incorrect. And when the solution is false, it returns back to the original position where it was called. It just iterates through the next item which is there in the possibilities list and goes on and on and on. Now this is the classic example of a recursive backtracking algorithm which will be helpful for us to solve the problem. Now let's see how it works. It has solved it. Now let's take a quick look at how it actually does. We'll put a breakpoint here, and let's see what happens. We'll put a breakpoint at false. We'll put a breakpoint at this false. Not this, and we'll put a breakpoint at this case, right? We'll debug this problem. Okay, so it has reached a situation where it is not an easy problem to solve, so it has come to the non-easy part of things. Now let's take a quick look at what is happening in the recursive stack. Now we'll be looking at this stack for checking how many calls are being made recursively, and we'll be checking the list of all possibilities. Right now, if you look at possibilities, these are the possibilities that we actually have. If you look at the first box, we have 1, 2, 5 and 6 which are possibilities. The next one which has 1 and 2 which are possibilities, and so on. Now let's see what the algorithm does. We'll be going through each one of these locations. If it is 0, then possibilities of ij is nothing but 1, 2, 5 and 6. For the first possibility, it will take it. The possibility is now 1. It will now put it in. Now once it puts in, it will again try and solve the problem, but this time the problem is already solved with the first position being blocked with 1, and then it goes again and then tries to solve the problem using the easy method. If it is not able to solve it, again it comes to the hard method, and now when it again hit a list of all possibilities, it took the first possibility and then it calls it again. Every time it calls it, just see the stack trace keeps on increasing, which means that every time I keep trying one possibility, it puts that item there and then keeps checking if the solution is going to come because of using this particular possibility. The moment, now what we'll do is we'll just run it, let it run for a while, let it keep doing its work. Now it has come to false, which means that it has reached a situation where the solution is incorrect. You'll find that one of them has actually been incorrectly placed, because of which it has decided that it is not correct. Now when that happens, it will come back to the old place where it was called and then go to the next possibility which was there. Now possibilities of I, 1 and 0. When it is been able to find the final solution, it actually returns true here. To summarize, we started off with an easy problem and we used two helper functions. One is to compute all the possibilities, and the second one which is to check whether the solution is correct, and use those two tools to solve the problem. For the easy problem, the solution is very simple. At each location where we need to find a solution, there will be only one option available which will be put in this place and it will solve the problem. For the hard problem, we needed to do a recursive backtracking algorithm wherein we went into each location which had more than one possibility, took one of the possibilities, put it in and saw if it led to the solution. If it did not, we came back to the place where we used the possibility, take the next option which is there and then go and solve it again. We keep doing this till we hit the right solution. That is why this is a brute force mechanism. So what did we learn from this? We learned about how to use recursion to solve a very interesting problem. There are better ways to solve this problem, but the whole intent of this particular video is to see how we can solve the Sudoku problem using a recursive algorithm. Try it out yourself and see. In case you have any doubts, please do post in the comments below. Thank you very much.